All right, welcome calculus. This is going to be section 3.2 where we introduce something called the power rule, making derivatives easier since sometime in the 17th century. So I'm going to start off by showing an example of a function that if I asked you to find the derivative of this function, it would take a lot of work. We'd have to go to our limit definition, and that's the limit of h approaches 0 of that f of x plus h minus f of x over h as h goes to 0. And to do that for this function, that's a lot of work. The f of x plus h part in particular, each of these x's turn into x plus h's, and you have to expand all those binomials. So I did it already here. Here's the function. I know it's kind of hard to read. Here's the derivative. The f of x plus h part, this red box, is all right here. So the x to the fifth becomes x plus h to the fifth. The x to the fourth becomes x plus h to the fourth. The x cubed becomes x plus h cubed, and so on. And this x plus h to the fifth, if I want to expand that binomial, I used Pascal's triangle here to expand out the x plus h to the fifth part. The x plus h to the fourth part, I expanded that binomial out. The blue one's here, the green one, the purple one's here, the orange one, and then the constant. This x to the fourth one, the green one, has this -3 that has to get distributed in. So this -3 gets distributed in down here. This 5 and the blue one has to get distributed, which I do here. And then the 2 and the 11 are also getting distributed in as well. So this entire thing is just the f of x plus h part. We have to subtract f of x from it. So I took this and wrote it all on a single line. And underneath, so this is f of x plus h right here. And this is f of x. So f of x is the x to the fifth, x to the fourth, 5x cubed, 2x squared, 11x, and 8. And when we're subtracting, all these signs become the opposite. So this becomes a minus, a plus, a minus, a minus, a plus, and a plus. Or excuse me, and a minus, what you see down here. I lined it up under f of x plus h because the x to the fifth minus x to the fifth will cancel out. The 3x to the fourth will cancel out. The 5x cubes, the 2x squareds, the 11x, and the 8s all cancel out. Everything left that didn't get canceled out has an h in there. This has an h, this has an h squared, this has an h cubed, h to the fourth, h to the fifth. This has an h squared, h cubed, h to the fourth, h squared, h cubed. And again, all of these have an h in them. So if I factor out those h's, everything that's left over is in this parenthesis right here. And once I factor out the h, these h's will cancel out. And so I'm left with this expression right here. Now, all of these terms have an h in them except for the first one. Or excuse me, not except for the first one. All these terms that have an h, as h goes to 0, become 0. So if h is 0, 10x cubed times 0 becomes 0. This h term is going to become 0. And everywhere we see an h, that term is going to become 0. So the only terms that survive are the 5x to the fourth, the 12x cubed, the 15x squared, the 4x, and the minus 11. So it looks like I did that kind of step here, but that's what we get when we take the derivative of this function, which is a lot of work. And the whole point of this quotient rule, power rule, is so that there's an easier way to do it, and I'm going to show you that now. So the power rule, your first derivative shortcut. So there's a couple of shortcuts where we won't have to use a limit definition, and this is the best one. If you're given a function of the form x to some power, then if I want to take the derivative of that, the derivative turns out to be whatever the exponent is, you multiply that by x, and the exponent drops down by 1 degree. And that's it. If you're given a power function, the derivative is going to be that power times the function, and then you subtract 1 from the degree. And that's our power rule. So the pseudo proof of it, like why is that the case? I'm gonna wait till we get to class to do this one. So you can stay tuned for this one. We'll get to that when I get you in class. A couple quick rules. Nothing here is going to be relevant until later on, but the idea is that I'm taking the derivative of a function and it's being multiplied by some factor. You can just take the derivative of the function and multiply the derivative by that same factor. And if I'm taking the derivative of a sum of functions, that's the same thing as taking the sum of the derivatives. That was also true for limits. So I'm just going to rewrite what the power rule is. If I have a function of the form x to the n, that implies that the derivative of that function is n times x to the n minus 1. So in this case, n equals 2. So the derivative of the function is going to be, if n is 2, it's going to be 2 times x to the 2 minus 1, which just becomes 2x. And that's it. We didn't need to do the limit definition. We can get it just as fast, or we can get it much faster doing it this way. In this case, n is 3, we have x to the third. So the derivative is going to be 3 times 5x to the 3 minus 1. And 3 times 5 we can simplify as 15. So this becomes 15x, 3 minus 1 is 2. 15x squared is the derivative. All right. Now, this one, example 3, f of x equals 14 is a constant function. That's a function of a horizontal line. The slope of a horizontal line is 0, and so the slope of this is going to be 0. Anytime you have a constant function, the slope or the rate of change is 0. You could think of it as 14x to the 0, because x to the 0 is 1, and 1 times 14 is 14, and then the derivative would be 0 times 14x to the 0 minus 1, which becomes even, so 0 minus 1 is negative 1, but 0 times anything is still going to give you 0. So you get 0 either way, but it's better to just memorize that anytime you have a constant function, the derivative is 0. Here I have a sum and a difference. I have a couple things going on here. Nothing to worry about. The derivative of sum is just a sum of the derivatives. So if I take the derivative of 2x squared, 2 times 2 is going to be 4x to the 2 minus 1, which is just 1, which I'm just going to write 4x. 4x, think of that as 4x to the first. 1 times 4 is 4, so it's going to be 4x to the 1 minus 1 is 0. And anything to the 0 is 1, so that just becomes 4x. That's going to be 4 times 1, which is just 4. And the derivative constant is 0, so we don't need to do minus 0. We're just going to leave it here. The derivative of 2x squared plus 4x minus 1 is 4x plus 4. Okay. Now, these 4 examples are still ones where I'm going to use the power rule, but we have to do a little bit of rewriting because we need it in the form x to the n. Then I can use the derivative rule that the derivative is going to be n times x to the n minus 1. So I'm going to rewrite this. 1 over x to the third is equivalent to x to the negative 3. Cross the line, change the sign. That's how we define negative exponents. So now that I have rewritten the function, the derivative of the function, now that n is negative 3, it's going to be negative 3x to the negative 3 minus 1. And negative 3 minus 1 is negative 4, so be careful with that. It's negative 4. And that's it. If you look in the back of the book, or like in an answer key somewhere, they'll probably rewrite it as negative 3 over x to the positive 4, so there's a positive exponent. You do not need to do that, but if you're ever looking up answers, they're equivalent. So number 6, same deal. We need to rewrite this so it's in the form x to the n, or x to some power, and the square root of x is equivalent to x to the 1/2. So if I want to find the derivative of that function, In this case, n is going to be 1/2. So it's going to be 1/2 x to the 1/2 minus 1. 1/2 minus 1 is negative 1/2. So this just becomes 1/2 x to the negative 1/2. And that's it. Okay. Again, in the back of the book, they'll probably write this as 1 over 2x to the positive 1/2. Or 1 over 2, and the x to the 1/2 is just the square root of x. So these are all equivalent, but you can just leave it like that. Another example where I want to rewrite it before I start. So again, the square root of x is x to the 1/2. Now I still don't have this as x to some power. I have 3 divided by x, but I can rewrite that as 3x to the negative 1/2. Now that I have it as x to some power, the derivative is going to be a piece of cake. So 3 times negative 1/2 is going to be negative 3/2 x to the negative 1/2 minus 1. Negative 1/2 minus 1 is negative 3/2. And that's it. Okay. Again, we could write it differently, but that's good for what we're looking for. This last one here, this first part is already in x to the n form, but this cube root of x is not. So I'm going to rewrite this. This is the function 3x to 7/8 plus the cube root of x is just x to the 1/3. So if I want the derivative of this function, 7/8 times 3 is 21/8. X to the 7/8 minus 1. 7/8 minus 1 is negative 1/8. The derivative of x to the 1/3 is going to be 1/3 x to the 1/3 minus 1. 1/3 minus 1 is negative 2/3. Nothing else to do here. There's our derivative. Okay. So another example where we want to rewrite it first. This is going to come up more often. A mistake that most people make on this type of problem is when I ask you to find the derivative and you feel comfortable with the power rule, you just want to take the derivative of the top, which the derivative of x squared is 2x and the derivative of 3 is 0. Then the derivative of the bottom, which the derivative of x is just going to be 1, and say that that's the derivative. But when you take the derivative of a quotient, it's not the case that you can just take the derivative of the top and divide it by the derivative of the bottom. There is a method for that, but we haven't gotten there yet. So in this particular problem, I need to rewrite this so that I have it of the form x to the n. So I'm going to rewrite this first as x squared over x plus 3 over x. We're getting closer. This is equivalent x squared over x. These x's just cancel out and you just get x, x to the first. 3 over x simplifies to 3x to the negative 1. I don't want to simplify, but you can rewrite it as 3x to the negative 1. So now that I have f of x, and it's in the form x to the n, think of that as 1 if you want, the derivative now is going to be a piece of cake. The derivative of x is going to be 1 x to the 0, and x to the 0 is just 1, so you just get 1. The derivative of 3x to the negative 1, negative 1 times 3 is negative 3, x to the negative 1 minus 1, which is just negative 2. So here is the derivative of that function. Again, there's other ways to simplify it, but I'm not worried about that at this point. First, we write it so that we use the power rule, and then we use the power rule. So now that we have that shortcut, this long derivative that you saw me take in the beginning of the video, we can take it really quickly now. The derivative of x to the 5th, the exponent is 5, so it's going to be 5x to the 5 minus 1 is 4. 3x to the 4th, 3 times 4 is 12. X to the 4 minus 1 is 3. 5x cubed, 5 times 3 is 15. X to the 2nd, 2 times 2 is 4. 2 minus 1 is 1, so that's going to be 4x. The derivative of negative 11x is just going to be negative 11. And the derivative of constant is going to be 0, which we don't need to write plus 0. And that is the derivative of the function, which takes seconds compared to using this limit definition That does work for all functions, but if it's just a polynomial function, it's a lot quicker way to get to that result. Anyways, so that's it for today, you guys. Have a nice night. Take care.